In Chapter 10, we're going to be looking at our first of organic synthesis chapters. In this chapter, we're going to be looking at nucleophilic substitution and elimination in the process of organic synthesis, and specifically focusing in on some other reactions that involve functional group transformations. Before we start looking at the actual reactions, we're first going to review the language of organic synthesis. Anytime we talk about synthesis, it is going to be a set of reactions that is used to make a desired product or molecule. The target molecule is the molecule that we're going to make through our synthesis. We will be starting with what we call or reference as starting material. These are the compounds that we will use to generate the target. It's what we initially put into our reaction flask. Starting materials are usually low cost and relatively small molecules, meaning they have relatively few carbon atoms, and we will build onto those carbon atom chains or alter functional groups through our synthetic process. Each synthesis is going to involve a variety of different reactions to get us from our starting material into our target. Each one of these reactions is referred to as a synthetic step. As we go through each individual reaction, we're going to make what we refer to as synthetic intermediates, or just an intermediate. This is a compound that is produced after one synthetic step that will be used as the reactant in the next synthetic step. So if we were to look at this as a scheme, we would have our starting material that we start with. Again, these are going to be relatively low carbon numbers and relatively low cost. We will then run a reaction and produce some type of intermediate. And let's reference this as reaction number 1. We will then use that intermediate in another reaction, we'll call this reaction number 2, to produce a different intermediate. And we can continue to go through this process until we finally get to a reaction that I'm going to label as reaction number 3 to get us into our target, or that ending material that we're looking for. So any of our syntheses can have anywhere from one reaction to as many reactions that we need to get us from our starting material to our final target. The process that I have up on the screen has 3 steps associated with it, or 3 synthetic steps, and it would have 2 intermediates. And again, we'll see a variety of different processes, different numbers of reactions as we complete our synthetic steps. When we're writing our reaction, each synthetic step will have the following information. It'll have the overall reactants. Remember, it may be more than one reactant that we put into our reaction flask. It'll tell us the reagents that we have to add, so any information that'll help us get from the starting material into the next compound. It'll also tell us a little bit about our reaction conditions, and it will give us the overall products. These reaction synthetic steps are very different than the reaction mechanism. Remember that reaction mechanism is going to show us how we convert from the reactants to the products or intermediates. And those will always use those curved arrow notations to show us how the electrons are moved as we go through. We may have multiple mechanistic steps for any one synthetic step in a reaction. Most of the time in our reactions, the byproducts, the leaving groups, and the spectator ions are often going to be emitted from the synthesis. So we can really focus on what are the reagents, reactants, and our final products. Oftentimes the byproducts, leaving groups, and spectator ions will be included in the mechanism as we interconvert from one thing to another. As we're writing those reactions, we do need to include our reagents and our conditions in the reaction itself. Oftentimes these are going to be found on the arrow as we go from our starting material to our ending material. Reagents are typically going to be listed on top of the arrow. This is common notation that is practiced by most scientists, but it is not a rigid guideline. These reagents will be things such as other reactants and other things that we need to put into our reaction flask that are actually involved in the reaction process. Underneath the arrow, we will typically put our conditions. Conditions could be anything from the solvent. Solvents will not play a role in the reaction itself, but oftentimes we need certain solvents in order for a reaction to happen. It could be things such as the temperature. Do we need to add heat? Does it need to be run at a very specific temperature? It could also tell us how long we're going to run the reaction. Any type of condition that we might need to know in order to run the reaction will typically be found underneath our arrow. We're also going to use numbers to denote multi-step sequences. So maybe we don't want to write out each individual step like I did on the previous slide. If that's the case, we may have our starting material listed, and then we'll have one arrow to get us to our final target, and I may use steps to tell you each reaction that we're going to run. And after each number, each step, I would list for you the reagents and or the conditions that are needed. So writing it this way, I still have a 3-reaction process or 3 synthetic steps that I need to go through. But I'm not going to show you each intermediate that I would produce after step number 1 and step number 2. But we would be using those intermediates to move on in the reaction process itself. As we get ready to look at our different types of reactions that we can have, there are 2 main classifications that we will be looking at. The first one's what we're going to be looking at in this chapter, and that's our functional group transformations. And this is where we're actually going to change from one functional group into another functional group. The carbon skeleton or the carbon chain will stay the same. It will remain unaltered. The other types of reactions that we'll be looking at in some future chapters are going to be carbon bond forming and carbon bond breaking. This is where we're actually going to alter the carbon skeleton. We're going to take those carbon-carbon sigma bonds and we're either going to break them or we're going to form new ones to alter the actual chain.